Welcome to today's deep dive. Today we are unpacking this really fascinating, honestly kind of rebellious draft of a blog post.
Yeah, it is definitely not your standard, dry physics paper.
Not at all.
Right.
It's by an author who goes by Zionad 2023, and the piece is actually titled Draft. Mr. Einstein slacking off 123. Let's make it an everyday composition.
Which is a bold title, right? Going right after
Oh,
Einstein.
absolutely. And our mission for this deep dive, for you listening at home, is to really strip away all that dense, intimidating physics jargon. We want to use the author's incredibly vivid, everyday imagery to just, rethink the entire fabric of reality itself.
Because the author sets up a thought experiment that forces us to question, well, our most basic perceptions of space and time.
Right. Because usually when we look at a photograph or, I don't know, a painting, we assume we're looking at a single frozen moment in time.
Exactly. Like someone just hit pause on the entire universe.
Yeah. It feels super intuitive to think we're seeing one specific universal now. But then, and this is what the blog post gets into, you step into theoretical physics and the geometry of light, and suddenly that now just shatters into a million pieces.
It completely falls apart. We're looking at a reality that is honestly a bit of a cognitive mirage.
A mirage. I love that. So to understand why this author thinks our perception of the present is flawed, we have to start with the physical reality of how we see.
Right. And the author sets up a scenario that is just brilliantly simple. So imagine a standard classroom.
Okay, got it.
Up at the front, there is a large, perfectly flat blackboard. And on that blackboard, someone has drawn a side view of a train and a set of train tracks.
Now, to actually see this drawing, you have to physically be in the room.
Yes, exactly.
You have to be sitting in a specific seat.
Yeah.
So the author asks us to imagine placing a camera eye, like a recording observer, right in that specific classroom seat.
And this is where it gets interesting. Think about the geometry of that room from the perspective of that camera eye. The physical distance from the camera's lens to the different parts of the drawing on that flat blackboard, it's not uniform.
It's not the same distance.
Right. If we look at the point where, say, the back wheel of the train touches the track, let's call that point A. The distance from our camera eye might be exactly 11 units of measurement.
Okay, 11 units.
But the distance to the front wheel of the train, point B, which is further off to the side of the board, that might be 12 units away.
Okay, let's unpack this for you listening, because this is crucial. It's exactly like sitting in a massive IMAX movie theater.
Oh, that's a perfect analogy.
Right. You're in your seat, dead center. The screen is massive and, mostly flat. The light bouncing off the far left or right edges of that giant screen literally has to travel a longer physical distance through the air to reach your eyeballs.
Compared to the light coming from the dead center of the screen.
Exactly. And because that physical distance is longer, the light from the edges takes a tiny microscopic fraction of a second longer to reach you.
And in everyday life, our brains just automatically stitch all that incoming data together. We completely ignore that micro delay.
We just watched the IMAX movie, and our cognitive processing tells us, hey, we're seeing the whole screen at exactly the same time.
Right, but if we connect this to the bigger picture in physics, distance literally is time.
Because light has a strict speed limit.
Exactly. So what the author is pointing out is that the image we perceive as a single, unified present moment is actually just a collage.
A collage of different pasts.
That's so trippy.
It really is.
Yeah.
Because light takes time to travel, you are never seeing the universe exactly as it is. You're seeing it as it was when the light left its surface.
So the back wheel of the train on that blackboard is actually slightly older to your eye than the center of the train.
Yes. Purely because of where it sits on the flat board relative to your position.
Wow. So the present doesn't actually exist as a flat picture. Treating a flat surface, like your standard Cartesian grid, everyday X and Y axis graph paper, as a single moment in time is just fundamentally flawed. It's completely flawed. Unless you are perfectly equidistant from every single point on that grid, you are receiving information from different points in the past.
You just can't look at a flat map and say, this is the state of the universe right now.
You can't, which begs the question.
How does the author fix this? Because we can't just leave our camera eye staring at a distorted timeline, right? Where the edges are always lagging behind the center.
Exactly. And the author comes up with a brilliantly creative solution to this unequal distance problem.
Yeah, they ask, what if we want the distance from all points on those drawn train tracks to our camera eye to be exactly the same?
Like a pendulum swinging, where the string length never ever changes.
Right. And to achieve that with the blackboard, we'd literally have to rip it off the wall and bend it.
We have to roll it. The author suggests rolling it into a cylinder with a radius of 10 units.
And to help us visualize this, they bring in this wild reference to René Magritte's surrealist painting, The Memory of a Saint.
Which is such a cool visual.
It is. For those trying to picture it, the painting depicts these heavy theatrical curtains that are rolled into a cylindrical stage.
Yeah, it looks almost like a wide tube standing upright on a stage.
Exactly. And inside that enclosed cylinder is a perfectly clear blue sky with clouds. So the author uses this painting as a spatial map for our thought experiment.
Right. We take our camera eye and we place it exactly at the center of this Magritte cylinder.
In Cartesian coordinates, that's x equals 0, y equals 0, z equals 0. Dead center.
And now the blackboard is curved perfectly around us.
So because of that curve, every single point on the horizontal plane of that blackboard is exactly 10 units away from our eye. The distance is finally equalized.
Yes. The light from the front of the drawn train and the back of the drawn train will reach us at the exact same instant. We have manufactured true simultaneity for that horizontal plane.
Okay, here's where it gets really interesting, though, because I have to push back a little on the author's setup here.
Okay, let's hear it.
The real world isn't a cylinder. I mean, we don't live inside a Magritte painting.
Right, obviously.
If we have to bend the literal world into a tube just to make the math clean and keep all the distances equal, aren't we just admitting that our standard flat map of the world is deeply inherently flawed? Like, we're contorting reality just to make our equations work.
That pushback hits the nail completely on the head. That is exactly the author's point.
Wait, really? That was a goal?
Yes. The flat Cartesian coordinate grid we all learned in high school geometry, it doesn't actually match the physical reality of how a single observer receives light in the universe.
Oh, wow. So we map the world flat, but we experience the world spherically.
Precisely. The math we use to describe space is fundamentally disconnected from how we actually observe space.
That makes so much sense.
The author argues that to truly represent what an observer sees at a given moment, meaning the light reaches the observer at the exact same instant, we actually need to treat this space as a spherical cap.
The spherical cap. Okay, so if you're listening and trying to picture the math, don't worry about the x and y coordinates. Just imagine standing inside a giant curved dome.
A dome is the perfect way to think about it. Because light radiates outward in a sphere, the points in space that are truly simultaneous to an observer form a curved surface.
So the author is basically methodically dismantling our reliance on flat, uniform grids when we talk about observation and the speed of light.
Absolutely.
Okay, I'm tracking with this. We've rolled up the blackboard. We're sitting under our spherical dome. But if our brains are easily fooled by a stationary flat screen or a drawing of a train, what happens when the objects we are observing are actually moving?
That is where the author takes us to the next layer of the experiment.
The purple LEDs.
Yes, the purple LEDs. Let's step into this new setup. Imagine we were in a room with no external velocity. It's a completely closed system, so we don't have to worry about the room moving through space.
Okay, closed room.
And inside this room, light travels at its constant speed, which physicists call c.
Right. And the author tells us to line up a vertical column of purple LED point lights. Tiny little bulbs.
Going straight up the z-axis.
Straight up from the floor to the ceiling. But we don't put them right in front of our nose. We push them back to a distance of 10 units away.
And here's the setup for the illusion. All of those purple LEDs in that vertical line are wired together so they turn on simultaneously.
At the exact same time.
Right. At exactly time 0, let's call it t equals 0, they all flash a massive instant vertical line of purple light.
But our boss, camera eye, the one sitting at our origin point of 0, 0, 0, doesn't actually see them all flash at once.
It physically cannot. Let's trace the path of the light. The LED at the very bottom of the column at floor level has a straight horizontal shot to our eye.
Because it's exactly 10 units away.
Exactly. So the light takes 10 units of time to arrive. It hits our eye at t equals 10.
But the LED way up at the top of the column, let's say it's 10 units high, the light from that top bulb doesn't get to travel a straight horizontal line.
No, it has to travel diagonally down to our eye.
It's forming the hypotenuse of a right triangle.
A triangle with a base of 10 and a height of 10. And mathematically, that diagonal hypotenuse is longer.
Right. It's the square root of 200, which comes out to roughly 14.1 units long.
So the light from that top bulb, even though it flashed at the exact same instant as the bottom bulb, doesn't arrive at our camera eye until t equals 14.1.
Which creates an incredible optical illusion.
It really does. To the human eye or the camera eye sitting in that seat, a simultaneous flash of a whole vertical line of lights doesn't look like a line at all.
It looks like a single dot of purple light starting at the bottom and moving upward over the course of 4.1 seconds.
A completely stationary flash is perceived as a moving object.
That is insane.
It actually brings to mind the French psychoanalyst Jacques Lacan. He argued that human reality is deeply fractured.
Oh, so...
Well, Lacan believed there is a fundamental gap between the actual physical, real, what is physically happening, and the image, what our brains piece together and perceive.
So the author of our source text is essentially applying this psychological concept to theoretical physics.
Precisely. What the camera actually perceives, that moving dot, is the cognitive image. It is a world built entirely out of delayed light.
But the mathematical real, the actual physical event, was a simultaneous flash.
Exactly. The map versus the territory. We are confusing the delayed image for the physical reality.
So to bridge that gap, to fix this moving dot illusion, the author introduces this wild mathematical concept that they call a cheat.
A massive cheat.
Yeah. Instead of relying on one boss camera eye waiting for delayed light, imagine we deploy a massive team of subordinate camera eyes.
We place these tiny subordinate cameras right up against every single purple LED on that vertical column.
So the instant the light flashes at t=0, the subordinate camera right next to it sees it, and then we give these subordinates a superpower.
They instantly teleport a report of that flash back to the boss camera. Zero delay.
Faster than the speed of light.
They completely bypass the physical laws of the universe to deliver information instantaneously.
So I was trying to picture this, and it's basically like having a massive team of reporters live tweeting a stadium event directly into your brain.
Oh, that's good.
Right. Like you don't have to wait for the sound of the crack of the bat to travel across the stadium to your ears. You instantly know exactly what happened in section 104 the millisecond it happened.
That analogy perfectly captures the cheat. And the author is pointing out that this teleporting of information is exactly how physicists and mathematicians build their coordinate maps.
Wait, really?
Yeah. When they look at an XYZ grid, they are assuming a God's eye view. They assume they instantly know the state of everything everywhere on that grid at t=0.
But they don't. No one does. No one has a God's eye view.
And that is the crux of it. The author is starkly separating these two worlds. There is the mathematical world, the map, where everything is known instantly. And then there is the physical, observable world, the territory, where every piece of information you ever receive is constrained and delayed by the speed of light.
And this assumption of a God's eye view is exactly what the author uses to challenge relativity. Because if you confuse the map with the territory, you run into massive problems.
Massive problems.
Which brings us to why the author firmly believes Albert Einstein was, quote, slacking off.
We are stepping into some heavy historical physics here.
Yeah, we are.
To understand the critique, we need to look at Einstein's famous thought experiment involving a moving train, which he used to define the concept of simultaneity for moving bodies.
Okay, so if I remember my high school physics correctly, Einstein used a moving train to prove that time is relative.
Right.
The standard idea is that if you have a moving train carriage and a light flashes in the exact center of that carriage, from the perspective of a passenger sitting inside, the light will hit both the front wall and the back wall of the train at exactly the same time.
Because the light source is in the middle and the speed of light is constant.
Exactly. The passenger sees the reflections return simultaneously. And Einstein argued that this internal consistency defines simultaneity for that moving frame of reference.
If you are inside the closed system of the train, the flashes hit the walls at the same time. But the author of our source text passionately disagrees with this foundational premise.
They call Einstein's definition flat out unreasonable.
Which is quite the statement.
It is, and their reasoning comes right back to the map and the territory. The author argues that we have to look at the medium the train is moving through, the electromagnetic field itself.
Let's say this train is moving incredibly fast, like 60% or 80% of the speed of light, just plowing through space.
Okay.
The author compares it to the Doppler effect for sound, but applied to light in a moving object. If the train is rushing forward through the electromagnetic field, the light bouncing off the front wall has to fight against the forward motion of the train to get back to the center.
Oh, I see.
Meanwhile, the light bouncing off the back wall is being rushed toward the center as the back of the train moves forward.
So objectively, from an external standpoint, the light hitting the front wall has to cover more actual distance through the field than the light hitting the back wall.
which means the light must take longer to complete its round trip depending on how fast the train is moving.
Wow.
The total time for the light to leave the center, hit the walls, and return should vary. It might take 25 seconds instead of 20 seconds, purely depending on the speed of the train through the electromagnetic space.
Now, we need to carefully frame this for you listening. We are not a physics peer review board,
No, definitely not.
and we are not taking sides on whether Einstein's century-old theory of relativity is fundamentally broken or if this author's alternative model is the new truth.
We are simply exploring the ideas presented in the text impartially.
Right.
And the author's fascinating perspective is that Einstein completely ignored the physical medium of the electromagnetic field. The author believes that Einstein artificially defined the light's return time as being identical in all moving trains, regardless of their speed through the field.
So by forcing that mathematical definition, the author argues, Einstein had to bend something else to make his equations work.
He had to conclude that time itself slows down for the outside world to accommodate this artificial rule he made for the inside of the train.
Unbelievable.
Yeah.
So in the author's view, Einstein committed the ultimate sin of the LED experiment. He confused the mathematical map with the physical territory.
He prioritized the clean, instantaneous math of a localized coordinate system, the inside of the train, over the messy, delayed reality of light actually traveling through a physical medium.
Mr. Einstein's slacking off. The author is basically saying Einstein took a shortcut.
He used the instant reporting cheat we talked about with the teleporting cameras.
He assumed a God's eye view of the train, rather than grappling with the actual delayed travel of light from a local point of observation.
It is a profound challenge, and it forces us to step back and look at our own perception.
So why does this dense, highly mathematical argument about coordinate spaces and light speed matter to you? Why should you care about Magritte cylinders and train tracks?
Well, it matters because it forces us to question our most foundational assumptions about reality. Are we ever experiencing the world as it truly is right now?
If every photon of light that hits your eye carries a different timestamp based on how far it traveled to reach you, the present isn't a single moment.
It's an aggregate.
Are we just living inside a delayed, slightly distorted map that our brain frantically stitches together from old light?
We think we are seeing the territory, but we are actually just looking at a biological approximation of the map.
It's a humbling realization. I mean, we've gone from the delayed light of a chalk drawing on a blackboard to rolling that blackboard into a theatrical stage just to equalize the delay.
We looked at the illusion of a moving dot created by simultaneous LED flashes.
And we explored the teleportation cheat that mathematicians use to ignore that illusion entirely.
All of it culminating in a really bold, unapologetic challenge to how Einstein defined time itself.
It is a massive intellectual journey from a simple classroom setting.
It really is. And before we wrap up, this journey raises an important question that builds on everything the author has laid out. I want to leave you with something to ponder regarding our modern lives.
Okay, lay it on us.
If our entire perception of the physical present is actually this mosaic of different paths based on physical distance, what does that mean for our hyper-connected digital world?
Oh, wow. I see where you're going with this.
Think about a global video call. You are sitting in New York, talking to someone in Tokyo.
Right.
The digital lag, the routing of data packets through fiber optic cables across the bottom of the ocean, bouncing off satellites, it creates an artificial extreme version of the author's blackboard problem.
It's the LED illusion on steroids.
Exactly. We already know that the physical universe prevents us from sharing a true, perfectly simultaneous now, even with the person sitting directly across the room from us.
Because their image is slightly delayed by the speed of light.
Right. But add digital latency to that. It makes you wonder, if physics prevents a shared present locally, are we ever truly sharing a present moment with anyone in the digital age?
Or are we just two isolated observers locked inside our own spherical caps, interacting with the ghostly, delayed echoes of each other?
Exactly. Are we ever really in the same now?
That is a thought that is going to keep me up at night. We are basically communicating by throwing postcards across a cosmic void, pretending we are holding hands.
It's a chilling way to look at a Zoom call.
It really is. Well, thank you so much for joining us on this deep dive into the architecture of space, time, and perception.
It's been a mind-bending ride.
Absolutely. Keep looking closely at the world, keep asking why things are the way they are, and most importantly, keep questioning the reality around you. We'll catch you on the next deep dive.